So let's take a look at hybridization theory from an organic chemistry point of view. So we're treating these orbitals on the atoms like wave functions. And just like any wave, like a water wave, these waves can come together in basically one of two ways. They can come together constructively, which is to say that they come together in phase, and we produce a new wave which is bigger and is basically the sum of its component parts. But we can also see waves at the other end of the spectrum coming together destructively or out of phase, where they would basically cancel each other out. And we can treat these orbitals like waves and see the hybrid orbitals which are produced. So first of all, let's think about the s atomic orbital coming together with one of the p atomic orbitals, treat them like wave functions and combine them together. Now we're using the colour to represent whether that part of the orbital is in phase or out of phase with a neighbouring orbital. So the blue part of the s orbital is in phase with the right hand side of the p atomic orbital, but that red colour tells us that that part of the orbital is out of phase with the s orbital it's coming together with. So for every atomic orbital that we use, we produce a hybrid orbital from that combination. So taking the s and one of the p's, we produce two hybrid orbitals. This is why we refer to this as sp hybridization. S and p tells us the kinds of atomic orbitals that were used for the hybridization. And because it's two orbitals, we produce two of these hybrid orbitals. And as they come together, the parts which are in phase enlarge that area of the orbital, and the parts that come together out of phase destruct and shrink that part of the orbital. So we produce two hybrid orbitals, one which focuses electron density on the right hand side of the nucleus, and one hybrid orbital that intensifies electron density on the left hand side of the nucleus being at the center of the crosshairs each time. So that's our sp hybridization. We look at those two hybrid orbitals together around the carbon nucleus. They get as far away from each other as possible. That ties in with Vesper theory, as we saw in Chemistry 151. And so the two hybrid orbitals stretch away around the nucleus as far away from each other as possible, and it creates this linear shape around the nucleus, and therefore a bond angle of 180 degrees. Remember, of course, with sp hybridization, it leaves two of the atomic orbitals in that p subshell which are not hybridized. One of those unhybridized p orbitals is above and below the plane, so it's getting as far away from the hybrid orbitals as possible, and that creates an angle between the unhybridized orbital and either one of the two hybrid orbitals of 90 degrees. Of course, there's a second atomic orbital which is unhybridized, it's still atomic, and that's at 90 degrees to both the hybrid orbitals and the other atomic orbital. So one of the atomic orbitals is above and below the plane of the nucleus, and one of the atomic orbitals is to the left and right, going into and out of the paper in front of us. So if we look at a molecule, a hydrocarbon molecule, let's think about how we could detect these sp hybridized atoms. And basically, we're looking to count the sigma bonds directly between two atoms and any lone pairs. And we're looking for a count of 2, which reflects the two atomic orbitals which have been used. So, as we look at the molecule here, the first sp hybridized carbon we can see is the carbon, which has got the single bond on one side and the triple bond on the other. A sigma orbital there, which uses one of the hybrid orbitals, And then for the other carbon-to-carbon bond, another sigma bond, one of the 3 lines, and then the other 2 lines are using the atomic orbitals, one of them above and below the plane, and one of them to the left and right of the plane. Looking for the next atom, which is sp hybridized, we have got the other carbon, which is part of the carbon-to-carbon triple bond, and that's the most common way of identifying sp hybridized carbons. We're looking for atoms which are part of an alkyne bond, carbon atoms which are part of a carbon-to-carbon triple bond. So when we only get a count of 2 from the sigma bonds and the lone pairs around the atom, that's normally an sp hybridized atom. Let's look at the next kind of hybridization, looking at sp2 hybridization, and as the name suggests, we use the s orbital and 2 of the p orbitals from the p subshell. We combine them together like wave functions, like water waves, and when they're in phase, like the blue parts are in phase together, they come together constructively, and when the blue and the red parts come together, they're coming together destructively or out of phase. And again, the number of atomic orbitals used will be equal to the number of hybrid orbitals which are produced. So with 3 atomic orbitals used, we get 3 hybrid orbitals. Okay, it's just not coming up there. And we look at these 3 hybrid orbitals which are produced. One of them intensifies the electron density to the right of the nucleus. One of them intensifies electron density to the left, and one of them intensifies electron density in front along the y-axis. So these 3 hybrid orbitals come together, and they come together, but they maximize distance between each other. And so these 3 hybrid orbitals come together in this trigonal planar shape, creating a bond angle each time of 120 degrees. Remember that there's still an atomic orbital which is unhybridized in all this, and that atomic orbital occupies the plane above the hybrid orbitals, so it's at 90 degrees to any one of the 3 hybrid orbitals, and it maximizes distance between each of the electron pairs. So we've got a trigonal planar shape around an sp2 hybridized carbon atom with just 1 atomic orbital above and below the plane. And again, as we look at an organic molecule, we count the number of sigma bonds and lone pair electrons to work out the level of hybridization. Because sp2, it uses 1 s orbital and the 2 of the 3 p orbitals, that's 3 altogether. We're looking for a count of 3 when we look at our organic molecule. So in this case, as we look through the molecule, we're looking for atoms with a count of 3 to match the 3 atomic orbitals that were used. And in this case, we get the carbon atom, which is part of the carbon-to-carbon double bond. There's 1 hybrid orbital used to make the carbon bond on the left. There's 1 hybrid orbital used to make the carbon-to-carbon bond on the right, and 1 hybrid orbital used for the carbon-to-hydrogen bond. That second bond, which is a pi bond, making up the rest of the double bond, that's using the atomic orbital above and below the plane. So therefore we don't have far to look to find the next sp2 hybridized carbon atom. It's the carbon next door, again part of the carbon-to-carbon double bond. And that's the most common sign that we can look for to find an sp2 hybridized carbon. We're basically looking at alkene molecules and looking specifically at the carbons which are part of the carbon to carbon double bond. Let's look at our last kind of hybridization, sp3 hybridization. And as the name suggests, we use the s atomic orbital and all three of the p atomic orbitals making up the p subshell in the second shell. And again, the number of atomic orbitals used tells us about the number of hybrid orbitals which are going to be produced. In this case, 1, 2, 3, 4 sp3 hybrid orbitals. And again, as we look at the coming together of the atomic orbitals, the parts which are blue are coming together in phase with the other blue parts and creating larger lobes for that part of the orbital. And when it's a blue part of an orbital coming together with the red part, these are parts which are signified as out of phase or destructively together. So we get these four unique orbitals, but they all look exactly the same as each other. They're just rotated around the nucleus at different angles. One side of the hybrid orbital enlarged, because this is when the orbitals are coming together in phase and constructively, and then one side of the hybrid orbital which is much smaller and has been shrunk because the atomic orbitals were coming together out of phase at that point. So as we put these four hybrid orbitals together, each of them known as an sp3 hybrid orbital, of course they come together around the nucleus and spread out as far apart as possible. As we talked about in class, we emphasize the larger enlarged lobe of the orbital, and we pretty much omit and delete that smaller part of the lobe, although it is there, just hidden underneath these larger enhanced in-phase parts. So as those four hybrid orbitals come together, they separate and get as far away from each other as possible around the nucleus, and it creates this tetrahedral shape around the atom, and it's creating a bond angle between one hybrid orbital and the next, a bond angle of 109.4 degrees, and this is creating this alkane shape around each carbon atom, this tetrahedral shape. So as we look at a hydrocarbon molecule and look for the atoms which are sp3 hybridized, because we used 1 and 3, 4 atomic orbitals, we're looking for a combination of 4 sigma and lone pairs around the atom to designate sp3 hybridization. So that's normally looking for carbons which have 4 sigma bonds. So carbon atoms which don't have any pi bonds. So there should be no double bonds and no triple bonds. So our first carbon is there with 4 sigma bonds, each one using one of the hybrid orbitals. So the first bond there, then a second, a third and a fourth hybrid orbital, giving us our sp3 hybridization. Then a second carbon there, and a third. We then bypass the double bonded carbons and then move to the single bonded carbon to the right, then bypass the triple bonded carbons and then switch back to the single bonded, giving us our last examples of sp3 hybridization. And so we're primarily looking at alkanes with 4 individual bonds. And that really gives us our 3 kinds of hybridization. The sp3 will normally have just single bonds. The sp2 will normally have a carbon which is part of a double bond. And our sp hybridization is normally carbons which are part of a carbon-to-carbon triple bond.